Secondly, the multiplication is not necessarily commutative. That is, it is not generally the case that AB equals BA, for all A, B. The first of these two issues turns out to be a relatively minor one, which will be dealt with in section 1.8. The latter is essential and, in many ways, is the heart of the subject. One might have expected an axiom stating that the involution is isometric. In fact, it is a simple consequence of the ones given, particularly the C condition. Proposition 1.1.2. If A is an element of AC algebra A, then number 6b A, number 6b equals number 6b A, number 6b. Proof. As A is a Banach algebra, number 6b A, number 6b 2 equals number 6b A at number 6b is less than or equal to number 6b A, number 6b, number 6b A, number 6b, and so number 6b A, number 6b is less than or equal to number 6b A, number 6b. Replacing a with a then yields the result. Next, we introduce some terminology for elements in AC algebra. For a given A in A, the element A is usually called the adjoint of A. The first term in the following definition is then rather obvious. The second is much less so, but is used for historical reasons from operator theory. The remaining terms all have a geometric flavor. If one considers the elements in B, H operators on a Hilbert space, each of these purely algebraic terms can be given an equivalent formulation in geometric terms of the action of the operator on the Hilbert space. Definition 1.1.3. Let A be AC algebra. 1. An element A is self-adjoint if A equals A. 2. An element A is normal if A equals A. 3. An element P is a projection if P2 equals P, that is, P is a self-adjoint idempotent. 4. Assuming that A is unital, an element U is a unitary if UU equals 1 equals UU, that is, U is invertible and U minus 1 equals U. 5. Assuming that A is unital, an element U is an isometry if UU equals 1. 6. An element U is a partial isometry if UU is a projection. 7. An element A is positive if it may be written A equals BB. For some B in A in this case, we often write it as greater than or equal to 0 for brevity. 1.2 Examples. Example 1.2.1. C. The complex numbers. More than just an example, it is the prototype. Example 1.2.2. Let H be a complex Hilbert space with inner product denoted less than, greater than. The collection of bounded linear operators on H, denoted by BH, is AC algebra. The linear structure is clear. The product is by composition of operators. The operation is the adjoint. For any operator on H, its adjoint is defined by the equation less than a she, eta greater than equals less than she, a eta greater than, for all she and eta in H. Finally, the norm is given by number 6b A, number 6b equals sup, number 6b A she, number 6b she element of H, number 6b she, number 6b is less than or equal to 1. For any A in B, H. Example 1.2.3. If n is any positive integer, we let M n C denote the set of n times n complex matrices. It is AC algebra using the usual algebraic operations for matrices. The operation is to take the transpose of the matrix and then take complex conjugates of all its entries. For the norm, we must resort back to the same definition as our last example. Number 6b A, number 6b equals sup, number 6b A she, number 6b. 2 she element of Cn, number 6b she, number 6b. 2 is less than or equal to 1. Where number 6b 2 is the usual number 62 norm on Cn. Of course, this example is a special case of the last using H equals Cn, and using a fixed basis to represent linear transformations as matrices. Example 1.2.4. Let X be a compact Hausdorff space and consider C X equals F, X right pointing arrow C F continuous. The algebraic operations of addition, scalar multiplication and multiplication are all pointwise. B is pointwise complex conjugation. The norm is the usual supremum norm. Number 6b f. Number 6b equals sup f x x element of x. For any f in C x. This particular example has the two additional features that Cx is both unital and commutative. Extending this slightly, let X be a locally compact Hausdorff space and consider C0 X equals F, X right pointing arrow C, F continuous, vanishing at infinity. Recall that a function f is said to vanish at infinity if, for every hash f greater than 0, there is a compact set K such that fx less than hash f for all x in xk. The algebraic operations and the norm are done in exactly the same way as the case above. This example is also commutative, but is unital if and only if x is compact, in which case it is the same as Cx. Example 1.2.5. Suppose that A, B are C algebras, we form their direct sum. A B equals A, B A element of A, B element of B. The algebraic operations are all performed coordinate-wise and the norm is given by number 6b A, B number 6b equals max, number 6b A, number 6b, number 6b B, number 6b. For any A in A and B in B. There is an obvious extension of this notion to finite direct sums. Also, if n is greater than or equal to 1 as a sequence of C algebras, their direct sum is defined as n infinity equals 1 an equals a 1, a 2. An element of an, for all n, lim number 6b an, number 6b equals 0. Aside from noting the condition above on the norms, there is not much else to add. Exercise 1.2.1. Let A equals C2 and consider it as an algebra with coordinate-wise addition, multiplication and conjugation. In other words, it is C1, 2, 1. Prove that with the norm. Number 6b alpha 1, alpha 2, number 6b equals alpha 1 plus alpha 2. A is not a C algebra. 2. Prove that number 6b alpha 1, alpha 2, number 6b equals max alpha 1, alpha 2 is the only norm which makes it into a C algebra. Hint: proceed as follows. First, prove that, in any C algebra norm, 1, 0, 1, 1, 0, 1 all have norm 1. Secondly, show that for any alpha 1, alpha 2 in A, there is a unitary U such that U alpha 1, alpha 2 equals alpha 1, alpha 2. From this, deduce that number 6b alpha 1, alpha 2 number 6b equals number 6b alpha 1, alpha 2 number 6b. Next, show that if A, B have norm 1 and 0 is less than or equal to T is less than or equal to 1, then number 6b ta plus 1 minus TB number 6b is less than or equal to 1. Finally, show that any elements of the form 1, alpha or alpha 1 have norm 1 provided alpha is less than or equal to 1. 1.3 Spectrum. We begin our study of C algebra with the basic notion of spectrum and the simple result that the set of invertible elements in a Untitled algebra must be open. While it is fairly easy, it is interesting to observe that this is an important connection between the algebraic and topological structures. Lemma 1.3.1. 1. If A is an element of a Untitled algebra AN, number 6b A minus 1, number 6b less than 1, then A is invertible. 2. The set of invertible elements of A is open. Proof. Consider the following series in A. B equals number 58 infinity. N equals 0. 1 minus A n. It follows from our hypothesis that the sequence of partial sums for this series is Cauchy and hence they converge to some element B of it. It is then a simple continuity argument to see that AB equals 1 minus of lim n number 58. n equals 0. 1 minus a n equals lim 1 minus a n plus 1 equals 1. A similar argument shows ba equals 1 and so a is invertible. If a is invertible, the map b right pointing arrow ab is a homeomorphism of a, which preserves the set of invertibles. It also maps the unit to a, so the conclusion follows from the first part. We now come to the notion of spectrum. Just to motivate it a little, consider the C algebra Cx, where X is a compact Hausdorff space. If f is an element of this algebra and lambda is in C, the function lambda minus f is invertible precisely when lambda is not in the range of f. This gives us a simple algebraic description of the range of a function and so it can be generalized. Definition 1.3.2. Let A be a untitled algebra and let A be an element of the spectrum of A, denoted spec A, is lambda element of C, lambda 1 minus A is not invertible. The spectral radius of A, denoted Ra, is sup lambda element of spec A, which is defined provided the spectrum is non-empty, allowing the possibility of Ra equals infinity. Remark 1.3.3. Let us consider for the moment the C algebra Mn(C), where n is some fixed positive integer. Recall the very nice fact from linear algebra that the following four conditions on an element of Mn(C) are equivalent. 1. A is invertible. 2. Cn right pointing arrow Cn is injective. 3. Cn right pointing arrow Cn is surjective. 4. Det A equals 0. This fact allows us to compute the spectrum of the element A simply by finding the zeros of det lambda minus A, which conveniently is a polynomial of degree n. The remark we make now is that in the C algebra B H, such a result fails miserably when H is not finite dimensional. First of all, the determinant function simply fails to exist, and while the first condition implies the next two, any other implication between the first three doesn't hold. We quote two fundamental results from the theory of Banach algebras, neither of which will be proved. Theorem 1.3.4. Let A be a untitled Banach algebra. The spectrum of any element is non-empty and compact. We will not give a complete proof of this result. Let us sketch the argument that the spectrum is compact. To see that it is closed, one shows that the complement is open, as an easy consequence of lemma 1.3.1. Secondly, if lambda is strictly greater than number 6b, then a computation similar to the one in the proof of lemma 1.3.1 shows that number 50 n lambda minus 1 minus n and is a convergent series in its sum is an inverse for lambda 1 minus a. Hence the spectrum of A is contained in the closed disk at the origin of radius, number 6b. As for showing the spectrum is non-empty, the basic idea is as follows. If A is in A and lambda 1 minus A is invertible, for all lambda in C, then we may take a non-zero linear functional phi and look at phi, lambda 1 minus of minus 1. One first shows this function is analytic. Then by using the formula from the last paragraph for lambda 1 minus of minus 1, at least for lambda large, it can be shown that the function is also bounded. By Leibniz's theorem, it is constant. From this it is possible to deduce a contradiction. The second fundamental result is the following. Theorem 1.3.5. Let A be an element of a untitled Banach algebra, the sequence number 6b and number 6b1. N is bounded by number 6b, number 6b decreasing and has limit Ra. In particular, Ra is finite and Ra is less than or equal to number 6b, number 6b. We will not give a complete proof C, but we will demonstrate part of the argument. First, as number 6b and number 6b is less than or equal to number 6b, number 6bn in any Banach algebra, the sequence is at least bounded. Furthermore, if lambda is a complex number with absolute value greater than lim sup number 6b and number 6b1 n, then it is a simple matter to show that the series infinity number 58 n equals 0. lambda minus n minus 1 an is convergent in a. Moreover, some basic analysis shows that lambda 1 minus a number 58 infinity n equals 0. Lambda minus n minus 1 and equals lim 1 minus lambda minus n and equals 1 minus 0 equals 1. It follows then that lambda 1 minus a is invertible and lambda is not in the spectrum of A. What the reader should take away from this argument is the fact that working in a Banach algebra, where the series has a sum, is crucial. With these results available, we move on to consider C algebras. Here, we see immediately important consequences of the C condition. Theorem 1.3.6. If A is a self-adjoint element of a unital C algebra A, then number 6b A, number 6b equals RA. Proof. As A is self-adjoint, we have number 6b A2, number 6b equals, number 6b A at number 6b equals, number 6b A, number 6b 2. It follows by induction that for any positive integer k, number 6b A2k, number 6b equals, number 6b A, number 6b 2k. By then passing to a subsequence, we have RA equals lim, number 6b, and number 6b 1. N equals lim k, number 6b A2k, number 6b 2 minus k equals, number 6b A, number 6b. Here we see a very concrete relation between the algebraic structure, in the form of the spectral radius, and the topological structure. While this last result clearly depends on the C condition in an essential way, it tends to look rather restrictive because it applies only to self-adjoint elements. Rather curiously, the C condition also allows us to deduce information about the norm of an arbitrary element, A, since it expresses it as the square root of the norm of a self-adjoint element, A. For example, we have the following two somewhat surprising results. Corollary 1.3.7. Let A and B be C algebras and suppose that ρ, a right-pointing arrow B, is a homomorphism. Then ρ is contractive. That is, number 6b ρ, a number 6b, is less than or equal to number 6b A, number 6b, for all in A in particular, we have number 6b ρ, number 6b, is less than or equal to 1. Proof. First consider the case that A is self-adjoint. As our map is a unital homomorphism, it carries invertibles to invertibles and it follows that spec ρ, a. Hence, we have number 6b ρ, a number 6b equals r ρ, a is less than or equal to ra equals number 6b A, number 6b. For an arbitrary element, we have number 6b ρ, a number 6b equals number 6b ρ, a number 6b 1. 2 equals number 6b ρ, a number 6b 1. 2 is less than or equal to number 6b A at number 6b 1. 2 equals number 6b A, number 6b. Corollary 1.3.8. If A is a C algebra, then its norm is unique. That is, if an algebra possesses a norm in which it is a C algebra, then it possesses only one such norm. Proof. We combine the C condition with the fact that A is self-adjoint for any A in A in Theorem 1.3.6 to see that we have number 6b A, number 6b equals number 6b A at number 6b 1. 2 equals sup lambda 1 minus a, not invertible. 1. 2. The right-hand side clearly depends on the algebraic structure of A and we are done. E. Number 50, exercise 1.3.1. With a as in lemma 1.3.1, prove that the sequence Sn equals n. N equals 1, 1 minus a, n is Cauchy. Exercise 1.3.2. For any real number t is greater than or equal to 0, consider the following element of M2, C. A equals number 14. 1T01, number 15. Dot. Find the spectrum of A, the spectral radius of A and the norm of A. Curiously, the last is the hardest. If you are ambitious, see if you can find two different methods, one using the definition and one using the C condition and the last theorem. Exercise 1.3.3. 1. Let A equals Cx, the algebra of complex polynomials in one variable, x. Find the spectrum of any non-constant polynomial in A. 2. Prove that there is no norm on A in which it is a C algebra. 3. Let B be the algebra of rational functions over C, that is, it is the field of quotients for the ring A of the last part. Find the spectrum of any non-constant rational function in B. 4. Prove that there is no norm on B in which it is a C algebra. 5. Find two things wrong with the following. If A is any algebra, then the formula given in the proof of 1.3.8 defines a norm which makes it into a C algebra. 1.4 Commutative C algebras. In section 1.2, we gave an example of a commutative, Untitled C algebra by considering Cx, where X is a compact Hausdorff space. In fact, all commutative, Untitled C algebras arise in this way. That is, the main goal of this section will be to prove that every commutative, Untitled C algebra A is isomorphic to Cx, for some compact Hausdorff space X. For the first part of this section, we will restrict our attention to commutative, Untitled C algebras, ending with the theorem above. Following on, we will also consider non-commutative C algebras and obtain some interesting consequences. Definition 1.4.1. Let A be an algebra over C. We define M(A) to be the set of non-zero homomorphisms to C. We remark that the notation comes from the fact that a homomorphism is a multiplicative linear map. Lemma 1.4.2. Let A be a untitled commutative C algebra and let phi be in M(A). 1. Phi A is in spec A for every A in A. 2. The map phi is bounded and number 6b phi number 6b equals 1. 3. For all A in A, we have phi A equals phi A. Proof. Consider the kernel of phi. It is clearly an ideal in A, and since phi is non-zero, it is a proper ideal and hence contains no invertible elements. For any A in A, phi A 1 minus A is clearly in the kernel of phi and hence is not invertible. Thus, phi A is in spec A and phi A is less than or equal to R A is less than or equal to number 6b A number 6b, from which it follows that phi is bounded and number 6b phi number 6b is less than or equal to 1. On the other hand, a non-zero multiplicative map must send the unit to a non-zero idempotent, and the complex numbers has only one such element. Phi 1 equals 1. Noting that number 6b 1, number 6b 2 equals number 6b 1 1, number 6b equals number 6b 1, number 6b implies that number 6b 1 number 6b equals 1, and hence number 6b phi number 6b is greater than or equal to phi 1 equals 1. For the last part, any A in A may be written B plus IC, where B equals A plus A2 and C equals IA minus IA2 are both self-adjoint. It suffices then, to prove that phi B is real, whenever B equals B. By using a power series for the exponential function, one sees that, for any real number t, ut equals eitb is a well-defined element of A. Moreover, an easy continuity argument shows that u minus t equals ut, and utu minus t equals 1. From this it follows that number 6b ut, number 6b equals, number 6b ut. Number 6b 1/2 equals 1. As phi is continuous, we have 1 equal to phi ut equals 8 phi b. For all real numbers t, it follows that phi b is real as desired. Lemma 1.4.3. Let A be a untitled commutative C algebra. The set M(A) is a weak compact subset of the unit ball of the dual space A. Proof. The Alolu theorem 2.5.2, page 70 of asserts that the unit ball is weak compact, so it suffices to prove that M(A) is closed. The weak topology is defined so that a net phi alpha converges to phi if and only if the net phi alpha converges to phi a for all in A. But then it is clear that if each phi alpha is multiplicative, says phi. This space M(A) will be our candidate compact, Hausdorff space. That is, we will show that A is isomorphic to C(M)(A). First, we stress that the topology on M(A) is the weak asterisk topology from the dual space of a. Let us remark that we can already see a map from the former to the latter. For any A in A, the formula of phi means that we can think of A as a function on M(A). It is the map a right pointing arrow that will be our isomorphism. Lemma 1.4.4. Let A be an element in a Untitled commutative C algebra. Evaluation at A is a continuous map from M(A) onto Spec A. Proof. Continuity is direct consequence of the definition of the weak topology. Secondly, for any phi in M(A), phi A is in Spec A from Lemma 1.4.2. Finally, we need to see that the map is onto. That is, let lambda be in Spec A. A simple Zorn's lemma argument shows that lambda 1 minus A is contained in a maximal proper ideal of A. Say I, we claim that I is closed. Its closure is clearly an ideal. Moreover, it cannot contain the unit since it is invertible. The invertibles are open and I contains no invertible. Thus, the closure of I is also a proper ideal and hence by maximality, it is equal to I. The quotient A I is then a field and also a Banach algebra, using the quotient norm. Let B be any element of this Banach algebra. As its spectrum is non-empty, 1.3.4, we have a complex number lambda such that lambda 1 minus B is not invertible. As we are in a field, we have lambda 1 minus B equals 0. Hence, we see that every element of AI is a scalar multiple of the unit. That is, AI equals C. The quotient map from A to C is then a non-zero homomorphism which sends it to lambda, since lambda 1 minus A is in I. The next result strengthens the conclusion, in that the evaluation map at A is actually injective, by adding the hypothesis that the commutative C algebra is generated by A and 1. It can either be described as the intersection of all C subalgebras which contain A, or as the closure of the algebra which is formed by taking the linear span of the unit and all products of A and its adjoint. From the latter description, it is clear that this algebra is commutative exactly when A commutes with its adjoint. Lemma 1.4.5. Let A be an element in a Untitled, commutative C algebra, A, and assume that A is the Banach algebra generated by A and 1. Then evaluation at A is homeomorphism from M(A) to Spec A. Proof. We know already that the map is continuous and surjective. It remains only to see that it is injective. But if phi and psi are in M(A) and phi A equals psi A, then it follows from 1.4.2 that phi A equals psi A and also that phi 1 equals psi 1 and hence phi equals psi since A and the unit generate A as a Banach algebra. We are now ready to prove our main result. Theorem 1.4.6. Let A be a commutative, Untitled C algebra. The function sending A in A to A in C M(A) defined by A phi equals phi. A phi element of M(A) is an isometric isomorphism from A to C M(A). Proof. The fact that A is a continuous function is a simple consequence of the definition of the weak topology. It is easy to see that the map is a homomorphism. That it is a homomorphism is a consequence of lemma 1.4.2. Our next aim is to see that is isometric. First, suppose that A is self-adjoint. From 1.3.6, we have number 6b. Number 6b equals R. A equals sup phi. A phi element of M A equals sup A phi element of M A equals number 6b A. Number 6b. For an arbitrary element, we then have number 6b A. Number 6b equals number 6b A at number 6b 1. 2 equals number 6b A at number 6b 1. 2 equals number 6b A at number 6b 1. 2 equals number 6b A number 6b. We must finally show that is onto. The range is clearly a untitled algebra. We will prove that the range separates the points of M, A. Assuming that this is true for the moment, we can apply the Stone-Weierstrass theorem, 4.3.4, page 146 of which states that a untitled subalgebra of C, M, A, which separates the points is dense. Moreover, since A is isometric and A is complete, the range is also closed and we are done. As for the claim that the range separates the points, let phi equals psi be two elements of M, A. The fact that they are unequal means that there exists an A such that phi, A equals psi, A. In other words, A, phi equals A, psi, and so A separates phi and psi. Now, let us again consider the situation where as B A untitled, not necessarily commutative, see algebra and let A be an element of B. We may consider A, the subalgebra be generated by A and 1. This subalgebra is commutative exactly when the three generators commute with each other, and this is exactly when A is normal, A equals A. Alternately, an element A in B is normal if and only if there exists a commutative, untitled C subalgebra element of AB. We can apply the last theorem to the C algebra A, as before, and lemma 1.4.5 provides us with a fine description of M, A. However, an interesting issue arises. If A is some element of A, it is conceivable that it has an inverse in B, but that inverse is not in A. In other words, whether or not A is invertible depends on whether we regard it as an element of A or B. In fact, this turns out not to be an issue. The answers are always the same. We will prove that in full generality, i.e. without assuming A is commutative in the next section. But for the moment, we need to worry about it in the special case where A is commutative. This same issue also means that the spectrum of A depends on whether we think of it in A or B. Let us briefly introduce some notation to deal with this. For A in A, let spec A be the set of complex numbers lambda such that lambda 1 minus A has no inverse in A, and let spec A be the set of complex numbers lambda such that lambda 1 minus A has no inverse in B. Obviously, the existence of an inverse in A implies one in B, and so spec A. Proposition 1.4.7. Let B be a untitled C algebra and let A be a commutative C subalgebra of B which contains the unit of B. An element of A has an inverse in A if and only if it has an inverse in B. In consequence, we have spec A equals spec B A. Proof. First, it is clear that if A has an inverse in A, it also has one in B. Hence, we have spec A spec B A. So let us assume that A has an inverse in B. It follows that A does also, A minus 1 equals, A minus 1, and so does A. We know from part 1 of lemma 1.4.2 and lemma 1.4.4 that spec A equals phi, a phi element of M, A. On the other hand, it follows from part 3 of lemma 1.4.2 phi, A equals phi, A equals phi, A is a non-negative real number. Also, part 2 of lemma 1.4.2 implies that phi, A is less than or equal to number 6b A at number 6b. It follows that spec B A at 0, number 6b A at number 6b. As we know that A is invertible, 0 is not in the spectrum, so spec B A at delta, number 6b A at number 6b. For some positive number delta, as lambda 1 minus number 6b A at number 6b, 1 minus A equals minus number 6b A at number 6b minus lambda 1 minus A, we see that spec B number 6b A at number 6b, 1 minus A equals number 6b A at number 6b minus spec B A at 0, number 6b A at number 6b minus delta. The element number 6b A at number 6b, 1 minus A is clearly self-adjoint, so we conclude that number 6b A at number 6b, 1 minus A number 6b is less than or equal to number 6b A at number 6b minus delta less than number 6b A at number 6b. It follows from part 2 of lemma 1.4.2 that, for any phi in M A, we have phi number 6b A at number 6b. 1 minus a less than number 6b A at number 6b. The left-hand side is simply phi number 6b A at number 6b. 1 minus a equals number 6b A at number 6b minus phi a 2. From these facts, we conclude that phi a equals 0. Another application of lemmas 1.4.2 AMD 1.4.4 implies that 0 is not in spec A, and so A is invertible in A. Now we return to the situation that A is a normal element of the Untitled C algebra B, and we attempt to exploit the commutative C algebra generated by A1, using the results we have so far. For any element of A, we can return to writing spec A. A very curious thing happens. The map a right pointing arrow of 1.4.6 is much less useful than its inverse. If f is any function in C spec A, using lemma 1.4.5 to identify spec A with M A, there is an element of A whose image under is exactly f. We will denote this element by f A. Definition 1.4.8. Let B be a Untitled C algebra and let A be a normal element of B. Let A be the C subalgebra of B generated by A and the unit. For each f in C spec A, we let f A be the unique element of A such that phi f A equals f phi A. For all phi in M A. The following now amounts to a restatement of 1.4.6 and 1.4.5. Corollary 1.4.9. Let B be a Untitled C algebra and let A be a normal element of B. The map sending f to f A is an isometric isomorphism from C spec A to the C subalgebra of B generated by A and the unit. Moreover, if f z equals number 50 k LAK LZKZL is any polynomial in Z and Z, then f A equals number 58 k L ac LAC A L. We take a slight detour by noting the following result. There is a more basic proof of this fact, but with what we have here, it becomes quite simple. Corollary 1.4.10. Let A be a normal element of the Untitled C algebra B, then A is self-adjoint if and only if spec A R. Proof. Under the isomorphism of 1.4.9, the restriction of the function f z equals z to the spectrum of A is mapped to A. Then A is self-adjoint if and only if f spec A equals f spec A, which holds if and only if spec A R. Corollary 1.4.11. Let A and B be Untitled C algebras and let ρ, a right pointing arrow B, be a Untitled C homomorphism. If A is a normal element of A, then spec ρ A spec A and f ρ A equals ρ f A for any f in C spec A. Proof. As we observed earlier, it is clear that ρ must carry invertible elements to invertible elements, and the containment follows at once. For the second part, let C and D denote the C subalgebras of A and B which are generated by A and the unit if A and ρ A and the unit of B, respectively. It is clear then that ρ C right pointing arrow D is a Untitled homomorphism. Suppose that psi is in M D. Then psi ρ is in M C, and we have psi ρ f A equals psi ρ f A equals f psi ρ A equals f psi ρ A. By definition, this means that ρ f A equals f ρ A. Exercise 1.4.1. Let X be a compact Hausdorff space. For each X in X, define phi X f equals fx. Prove that phi X is in M C X, and that X right pointing arrow phi X is a homeomorphism between X and M C X. Hint to show phi is surjective. The Rice representation theorem identifies the linear functionals on C X for you. You just need to identify which are multiplicative. Exercise 1.4.2. Suppose that X and Y are compact Hausdorff spaces and ρ C X right pointing arrow C Y is a Untitled homomorphism. 1. Prove that there exists a continuous function h, y right pointing arrow x such that row f equals fh, for all f in Cx. 2. Prove that this statement may be false if row is not unidel. 3. Give a necessary and sufficient condition on H for row to be injective. 4. Give a necessary and sufficient condition on H for row to be surjective. Exercise 1.4.3. Let B be the C algebra of bounded functions on 0, 1 with the supremum norm. Let Q equals K2 minus N K element of Z, N is greater than or equal to 0 intersection 0, 1. 1. Let A be the linear span of all functions of the form chi S, T chi T, 1 where S, T are in Q. Prove that A is a algebra. 2. Let A be the closure of A is the supremum norm, which is a C algebra. Prove that A contains C, 0, 1. 3. Prove that for all F in A and S in Q, lim x right pointing arrow S plus F x, x li right pointing arrow MS minus F x. Both exist. 4. Let H, M A right pointing arrow 0, 1 be the map given in the last exercise and the inclusion C, 0, 1 A describe M A and H. Exercise 1.4.4. Let B be a unidel C algebra and suppose A is a self-adjoint element and 1. 4 greater than hash F greater than 0 such that number 6b A minus A2, number 6b less than hash F. 1. Let F x equals x minus x2. Prove that f x is greater than or equal to min. Number 1a x. 2. 1 minus x2. Number 1b. Comma. For all x in R. 2. Prove that spec A minus 2 hash F 2 hash F union 1 minus 2 hash F 1 plus 2 hash F. 3. Find a continuous function g on spec A with values in 0, 1 such that g x minus x less than 2 hash F for all x in spec A. Also explain why there is no such function if spec A is replaced by 0, 1. 4. Prove that there is a projection P in B such that number 6b A minus P, number 6b less than 2 hash F. 1.5 Further consequences of the C condition. In this section, we will prove 3 more important results on the structure of C algebras. The first is a nice and somewhat surprising extension of our earlier result that any homomorphism between C algebras is necessarily a contraction, corollary 1.3.7. If we additionally assume the map is injective, then it is actually isometric. Lemma 1.5.1. Let A and B be unidel C algebras and rho, a right pointing arrow B be an injective, unidel homomorphism. Then for any normal element in A, we have spec A equals spec rho A. Proof. As rho maps invertible elements to invertible elements, it is clear that spec rho A spec A. Let us suppose that the containment spec rho A spec A is proper. Then we may find a non-zero continuous function f defined on spec A whose restriction to spec rho A is 0. Then we have f A equals 0 while, using corollary 1.4.9, we have rho f A equals f rho A equals 0. Since f spec rho A equals 0, this contradicts the hypothesis that rho is injective. Theorem 1.5.2. If A and B are unidel C algebras and rho, a right pointing arrow B is an injective homomorphism, then rho is an isometry, that is, number 6b rho A number 6b equals number 6b A number 6b for all A in A. Proof. The equality number 6b rho A number 6b equals number 6b A number 6b for a self-adjoint element follows from theorem 1.3.6 and lemma 1.5.1. For arbitrary A, we have number 6b A number 6b 2 equals number 6b A at number 6b equals number 6b rho A number 6b equals number 6b rho A number 6b equals number 6b rho A number 6b 2 and we are done. Earlier, we defined the spectrum of an element of an algebra. The fact that the definition depends on the algebra in question is implicit. As a very simple example, the function f(x equals x2 plus 1) is invertible when considered in the ring of continuous functions on the unit interval, c, 0, 1, but not as an element of the ring of polynomials, c, x. Rather surprisingly, this does not occur in C algebras. More precisely, we have the following. Theorem 1.5.3. Let B be a untitled C algebra and let A be a C subalgebra of B containing its unit. If A is any element of A, then its spectrum in B coincides with its spectrum in A. Proof. It suffices to show that if A is any element of A which has an inverse in B, then that inverse actually lies in A. In the case that A is normal, this follows from lemma 1.5.1 applied to the inclusion map of A in B. For arbitrary A, if A is invertible, then so is its inverses, A minus 1, and hence A is also invertible. As A is self-adjoint and hence normal, and since it clearly lies in A at minus 1 also lies in A, then we observe A minus 1 equals A minus 1, A minus 1 equals A minus 1, which obviously lies in A. The property of the conclusion of this last theorem is usually called spectral permanence. There is a simple, but useful consequence of this fact in Theorem 1.4.9, usually known as the spectral mapping theorem. Corollary 1.5.4. Let A be a normal element of a untitled C algebra B for any continuous function f on spec A. We have spec f A equals f spec A. That is, the spectrum of f A is simply the range of f. Proof. We have already noted the fact that for any compact Hausdorff space X and for any f in C X, the spectrum of f is simply the range of f, Fx. We apply this to the special case of f in C spec A to see that the spectrum of f is f spec A. Since the map from C spec A to the C algebra generated by A is an isomorphism and it carries f to f A, by definition, we see that spec f equals spec f A. The conclusion follows from the fact that the spectrum of A is the same in the C algebra B as it is in the C subalgebra. Exercise 1.5.1. Show that Theorem 1.5.3 is false if A and B are simply algebras over C. In fact, find a maximal counterexample, a B such that for every element of A, which is not a multiple of the identity, its spectrum in A is as different as possible from its spectrum in B. 1.6 Positivity. Let us begin by recalling two things. The first is the definition of a positive element in AC algebra given in 1.1.3. An element in AC algebra is positive if A equals BB. For some B in A, observe that this means that A is necessarily self-adjoint. Secondly, we recall corollary 1.4.10. A normal element of a untitled C algebra is self-adjoint if and only if spec A. Our goal now is to provide a similar, spectral, characterization of positivity for normal elements. Our main result, Theorem 1.6.5, states that a self-adjoint element in an untitled C algebra is positive if and only if spec A 0, infinity. Along the way, we will prove a number of useful facts about positive elements in an untitled C algebra. Lemma 1.6.1. Let A be a self-adjoint element of an untitled C algebra A. 1. Let f(x equals max x) 0 and g(x equals max minus x) 0 for x in R, then f a g a are both positive. We have A equals f a minus g a af, A equals f a 2. Ag A equals minus g a 2. F a g a equals 0. 2. If spec A 0, infinity, then A is positive. Proof. It is clear that f and g are continuous functions on the spectrum of A, each is real valued. Fx minus gx equals x, xfx equals fx2, xgx equals minus gx2, and fxgx equals 0, For all x in R, corollary 1.4.9 then implies that f, a, g, a are self-adjoint elements of A, satisfying the desired equations. Since f(x) is positive, it has a square root, and it follows that f(a) equals square root f(a)(2) equals opening parenthesis square root f(a) square root f(a) is positive. The same argument shows g(a) is positive. For the second statement, it suffices to notice in the proof above that if spec a 0, infinity, then g(a) equals 0. The following statement has a very easy proof, which is a nice application of the spectral theorem. Moreover, the result is a very useful tool in dealing with elements with positive spectrum. Lemma 1.6.2. Let A be a self-adjoint element of a Untitled C algebra. The following are equivalent. 1. Spec a 0, infinity. 2. For all t is greater than or equal to number 6b a, number 6b, we have number 6b t minus a, number 6b is less than or equal to t. 3. For some t is greater than or equal to number 6b a, number 6b, we have number 6b t minus a, number 6b is less than or equal to t. Proof. Since the spectrum of A is a subset of the reals and the spectral radius of A is its norm, spec a minus number 6b a, number 6b, number 6b a, number 6b. We consider the function ft x equals t minus x, for values of t is greater than or equal to number 6b a, number 6b. The function is positive and monotone, decreasing on minus number 6b a, number 6b, number 6b a, number 6b. Hence, the norm of the restriction of ft to the spectrum of A is just its value at the infinium of spec a. In view of corollary 1.4.9, number 6b t minus a, number 6b, is also the value of ft at the infinium of spec a. Finally, notice that ft x is less than or equal to t if and only if x is greater than or equal to 0. Putting this together, we see that the minimum of spec A is negative if and only if number 6b t minus a, number 6b greater than t. Taking the negations of both statements, spec a 0, infinity if and only if number 6b t minus a, number 6b is less than or equal to t. This holds for all t is greater than or equal to number 6b a, number 6b. Here is one very useful consequence of this result. Proposition 1.6.3. If A and B are self-adjoint elements of the Untitled C algebra A and spec A, spec B, 0, infinity, then spec A plus B, 0, infinity. Proof. Let t equals number 6b a, number 6b plus number 6b b, number 6b, which is evidently at least number 6b a plus b, number 6b. Then we have number 6b t minus a plus b, number 6b equals number 6b, number 6b a, number 6b minus a plus number 6b b, number 6b minus b, number 6b is less than or equal to number 6b, number 6b a, number 6b minus a, number 6b plus number 6b, number 6b b, number 6b minus b, number 6b is less than or equal to number 6b a, number 6b plus number 6b b, number 6b equals t. Where we have used the last lemma in moving from the second line to the third. The conclusion follows from another application of the last lemma. Before getting to our main result, we will need the following very basic fact regarding the spectrum. Lemma 1.6.4. Let A, B be two elements of a Untitled algebra A, then we have spec AB 0 equals spec BA 0. Proof. It clearly suffices to prove that if lambda is a non-zero complex number such that lambda minus AB is invertible, then lambda minus BA is invertible also. Consider x equals lambda minus 1 plus lambda minus 1b, lambda minus AB minus 1a. We see that x lambda minus ba equals lambda minus 1 plus lambda minus 1b lambda minus ab minus 1 of lambda minus ba equals 1 minus lambda minus 1 ba plus lambda minus 1b lambda minus ab minus 1 lambda a minus aba equals 1 minus lambda minus 1 ba plus lambda minus 1b lambda minus ab minus 1 lambda minus ab a equals 1 minus lambda minus 1 ba plus lambda minus 1 ba equals 1. A similar computation which we omit shows that lambda minus ba x equals 1 and we are done. We are now ready to prove our main result. Theorem 1.6.5. Let A be a self-adjoint element of a untitled C algebra, then A is positive if and only if spec A 0, infinity. Proof. The if direction has already been done in lemma 1.6.1. Let us now assume that A equals BB, for some B in A using the notation of 1.6.1, consider C equals BG A. Then we have CC equals GA BBG, A equals GA AG, A equals minus GA 3. Write C equals D plus IE, where D, E are self-adjoint elements of A. A simple computation shows that CC equals D2 plus E2 minus CC equals D2 plus E2 plus GA3. As the functions x2 and gx3 are positive, it follows from corollary 1.5.4 that each of D2, C2 and GA3 has spectrum contained in 0, infinity. By lemma 1.6.3, so does CC. On the other hand, again using corollary 1.5.4, we have spec CC equals spec minus GA3 minus infinity, 0. We now appeal to lemma 1.6.4 using E equals C, B equals C to conclude that spec CC equals spec CC equals 0. But this means that minus GA3 equals CC equals 0 and it follows that GA equals 0. This implies that the restriction of G to the spectrum of A is 0, which means spec A 0, infinity, and we are done. It is worth mentioning the following rather handy consequence. Corollary 1.6.6. If A is a normal element in a untitled C algebra B and F is a real-valued function on spec A, then Fa is self-adjoint. Similarly, if F is positive, then Fa is positive. Proof. We know that spec Fa equals F spec A from Theorem 1.5.4. Moreover, since Fa lies in the C algebra generated by A and the unit, which is commutative, it itself is normal. The two statements now follow from corollary 1.4.10 and corollary 1.6.5. Exercise 1.6.1. Let A be a untitled C algebra and suppose A is in a let f x equals square root x. X is greater than or equal to 0 and define A equals f A. 1. Show that if A is invertible, so is A. 2. Show that if A is invertible, then U equals A minus 1 is unitary. 3. Prove that if A is invertible, U and A commute if and only if A is normal. The expression A equals U A is usually called the polar decomposition of A. 1.7 Finite dimensional C algebras. In this section, we investigate the structure of finite dimensional C algebras. The main objective will be the proof of the following theorem, which is a very satisfactory one. Theorem 1.7.1. Let A be a untitled, finite dimensional C algebra. Then there exist positive integers k and n1, nk such that A equals k equals 1 mnk c. Moreover, k is unique and n1, nk are unique, up to a permutation. The theorem is also valid without the hypothesis of the C algebra being untitled. In fact, every finite dimensional C algebra is untitled, as a consequence of the theorem, but we do not quite have the means to prove that yet, so we content ourselves with the version stated above. At this point, the reader has a choice. The first option is to simply accept the result above as a complete classification of finite dimensional C algebras and then move on to the next section. The other option, obviously, is to keep reading to the completion of the section and see the proof. This brings up the question, is it worth it? Aside from the simple satisfaction of having seen a complete proof, there are 2 points in what follows which should be drawn to the reader's attention. The first point is some simple calculus for rank 1 operators on Hilbert space. This is not particularly deep, but the notation is useful and some simple facts will be assembled which will be used again later, beyond the finite dimensional case. The second point is that the proof of the main result is built around the existence of projections in a finite dimensional C algebra. In general, C algebras may or may not have non-trivial projections. As an example, Cx, where X is a compact Hausdorff space, has no projections other than 0 and 1 if and only if X is connected. However, the principle which is worth observing is that an abundance of projections in a C algebra can be a great help in understanding its structure. Before we get to a proof of this, we will introduce some useful general notation for certain operators on Hilbert space. Definition 1.7.2. If H is a Hilbert space and xi, eta are vectors in H, then we define xi eta, H right pointing arrow H by. Xi eta zeta equals less than zeta, eta greater than xi, zeta element of H. It is worth noting that if H is just Cn, for some positive integer n, then we can make use of the fact that the matrix product of an I times J matrix and a J times K matrix exists. With this in mind, if xi and eta are in Cn, which we regard as n times 1 matrices, then xi t eta is a 1 times 1 matrix while zt is an n times n matrix. Here xi t denotes the transpose of xi. The formula above just encodes the simple consequence of associativity. Zt zeta equals xi eta t zeta. Lemma 1.7.3. Let xi, eta, zeta, omega be vectors in the Hilbert space H and let a be in B H. We have 1. Xi eta is a bounded linear operator on H and number 6b xi eta, number 6b equals, number 6b xi, number 6b, number 6b eta, number 6b. 2. Xi eta H equals span, xi provided eta equals 0. 3. Xi eta equals eta xi. 4. Xi eta zeta omega equals less than zeta, eta greater than xi omega. 5. Xi eta equals a xi eta, 6. Xi eta a equals xi a eta. Moreover, if xi 1, xi 2, xi n is an orthonormal basis for H, then number 58 n. I equals 1. A xi I equals a. For any a in B H. In particular, the linear span of xi j. 1 is less than or equal to I, j is less than or equal to n. Is B H and number 58 n. I equals 1. Xi equals 1. We start toward a proof of the main theorem above by assembling some basic facts about finite dimensional C algebras. The main point of the following result is that general normal elements can be obtained as linear combinations of projections. Lemma 1.7.4. Let A be a unidal finite dimensional C algebra. 1. Every normal element in A has finite spectrum. 2. Every normal element of A is a linear combination of projections. Proof. For a normal, from 1.4.9, we know that C spec A is isomorphic to AC subalgebra of A, which must also be finite dimensional. It follows that spec A is finite. For each lambda in spec A, let P lambda be the element of C spec A, which is 1 on lambda and 0 elsewhere. As spec A is finite, this function is continuous. As a function, this is clearly a self-adjoint idempotent, so the same is true of P lambda A. Moreover, it follows that number 58. Lambda element of spec A. Lambda P lambda Z equals Z. For all Z in spec A. It follows from 1.4.9 that number 58. Lambda element of spec A. Lambda p lambda A equals A. Roughly speaking, we now know that a finite-dimensional C algebra has a wealth of projections. Analyzing the structure of these will be the key point in our proof. Lemma 1.7.5. Let A be a C algebra. The relation defined on projections by P is greater than or equal to Q if PQ equals Q, and hence after taking adjoints QP equals Q also, is a partial order. We leave the proof as an easy exercise. Lemma 1.7.6. Let A be a C algebra. 1. For projections P, Q and A, P is greater than or equal to Q if and only if PAP QAQ. In particular, if PAP equals QAQ, then P equals Q. 2. If PAP has finite dimension greater than 1, then there exists Q equals 0 with P is greater than or equal to Q. 3. If A is unital and finite dimensional, then it has minimal non-zero projections in the order is less than or equal to. Proof. First, suppose that P is greater than or equal to Q. Then we have QAQ equals PQAQ PAP. Conversely, suppose that PAP QAQ. Hence, we have Q equals QQQ element of QAQ PAP, so Q equals PAP, for summa in A then PQ equals PPAP equals PAP equals Q. For the last statement, if PAP equals QAQ, then it follows from the first part that P is less than or equal to Q and Q is less than or equal to P, hence P equals QP equals Q. A moment's thought shows that PAP is an algebra. It contains PPP equals P, which is clearly a unit for this algebra. If it is finite dimensional, then it is closed and hence is a C subalgebra. We claim that if a self-adjoint element of PAP, say A, has only one point in its spectrum, then that element is a scalar multiple of P. Let spec A equals lambda. Then functions f z equals z and g z equals lambda are equal on spec A. So by corollary 1.4.9, f A equals g A. On the other hand, corollary 1.4.9 also asserts that f A equals A while g A equals lambda p. Our claim follows, and this means that if every self-adjoint element of PAP has only one point in its spectrum, that PAP is spanned by P and one-dimensional. So if PAP has dimension greater than 1, we must have a self-adjoint element, A, in PAP with at least 2 points in its spectrum. Choose a surjective function, f, from spec A 2, 0, 1. It is automatically continuous on spec A. Q equals f A is a projection which is non-zero. As Q is in PAP, we have PQ equals Q. For the last statement, we first notice that since A is unital, it contains non-zero projections. Suppose that P is any non-zero projection in A, so PAP has dimension at least 1. If this dimension is strictly greater than 1, we may find Q as in part 2. So Q is non-zero, and since Q equals P, QAQ is a proper linear subspace of PAP, so dim QAQ less than dim PAP. Continuing in this fashion, we may eventually find Q such that dim QAQ equals 1. Hence, Q is minimal in the order is less than or equal to among non-zero projections. We will consider non-zero projections P which are minimal with respect to the relation is greater than or equal to. From the last result, we have PAP equals CP, for any such projection. Lemma 1.7.7. Suppose that P1, P2, Pk are minimal, non-zero projections in A with Pi app j equals 0, for A equals j. Then P1, Pk are linearly independent. A finite set of minimal projections satisfying the hypothesis will be called independent. Proof. If some Pi can be written as a linear combination of the others, then we would have CPI equals Pi app I equals PIA. Number 58. J equals I. Alpha JPJ. Number 58. J equals I. Pi app J equals 0. A contradiction. Lemma 1.7.6 guarantees the existence of minimal, non-zero projections in a untitled, finite-dimensional C algebra. A lemma 1.7.7 shows that an independent set of these cannot contain more than A elements, and it follows that we may take a maximal independent set of minimal, non-zero projections and it will be finite. Theorem 1.7.8. Let A be a finite-dimensional C algebra and let P1, P2, Pk be a maximal set of independent minimal non-zero projections A. Which one is less than or equal to K is less than K. K is a finite-dimensional Hilbert space with inner product less than A. B greater than Pk equals Ba. For all A, B in app K. 2. For each one is less than or equal K is less than or equal to K, app Ka, meaning the linear span of elements of the form app Ka, number 30, with A number 30, in A, is untitled C subalgebra of A3. K equals 1 app Ka equals A. 4. For each one is less than or equal to K is less than or equal to K, define the map pi K. A right pointing arrow B, app K, defined by pi K A B equals ab, for A in A and B in app K. Then pi K is a homomorphism and its restriction to app LA is 0 for L equals K and an isomorphism for L equals K. Proof. For the first statement, if A, B are in app K, then A equals app K, B equals BPK and so B equals BPK, app K equals PKB app K element of PK app K equals CPK, so the scalar less than A, B greater than as described exists. This is clearly linear in A and conjugate linear in B. It is clearly non-degenerate, for if less than A greater than equals 0, then A equals 0 which implies A equals 0. Choose Bk to be an orthonormal basis for app K, which means that for any A in app K, we have number 58. B element of Bk. B equals number 58. B element of Bk. B less than A, B greater than Pk equals number 58. B element of Bk. Less than A, B greater than Bpk equals number 58. B element of Bk. Less than A, B greater than B equals A. Next, we define Qk equals number 58. B element of Bk. B equals number 58. B element of Bk. Bpkb. It is clear that Qk is self-adjoint in app Kan. From above, Qka equals A, for any A in app K. Now if A number 30, are in A, we have Qk APK at number 30 equals Qk APK at number 30 equals APK at number 30. And APK at number 30 Qk equals Qk at number 30 Pk at equals at number 30 Pk at equals APK at number 30. So that Qk is a unit for app Ka. This completes the proof of part 2. In particular, we note that Qk Pk equals Pk. Since Pk app L equals 0 for all K equals L, we see that app Ka app La equals 0 as well. From this, we also see that Qk app L equals 0 and Qk app La equals 0 for K equals L. In particular, the projections Qk are pairwise orthogonal. Consider Q equals number 50. K equals 1 Qk, which is clearly a central projection. We claim that it is the identity for A. If not, there is an element B in A with BQ equals B, and so B minus BQ is a non-zero element in the set. Q equals a element of A Ka equals 0. It is a simple matter to verify that Q is a C subalgebra of A and is obviously finite dimensional. If it contains a non-zero element, then it contains a non-zero minimal projection, say P. Then for any K equals 1, 2, K, we have PQK is less than or equal to PQ equals 0, and so PQK equals 0. It then follows that PAPK equals PQK APKA equals 0. The set of projections P1, PK is an independent set of non-zero minimal projections, contradicting the maximality of P1. Pk. We conclude that Q is the identity of A, as desired. In consequence, we have A equals number 20, number 58, K, QK, number 21. A equals K, K equals 1 QK, A equals